good afternoon, good night, or good morning, everybody. I would like to share with you my research works about the shared memory materials and applications. So let's go. Okay, as indicated here, there are two focus of my research. That is, one is the materials from a materials aspect, shared memory materials, and the other is actually I put more efforts on applications of shared memory materials. Of course, the first is that what are shared memory materials? Here we have a video. This is a piece of nickel titanium shared memory alloy. As we actually we roll it, and then upon heating hot water, it recovers its original shape. And then if you take it out, it's curved a little bit. So if you take it out, it curved a little bit because of cooling. And if you dip inside of hot water again, it's going to become kind of straightened a bit. So the reversible motion, as you can see, the later part, that is called the two-way shared memory effect. And the first part actually we wrote significantly. That part actually is about the one-way shared memory effect. So the material, this piece of nickel titanium shared memory alloy, combines with together with the one-way shared memory effect and two-way shared memory effect. So here we have definition of shared memory materials. After being severely and quasi-plastically distorted, shared memory materials are able to recover their original shapes at the presence of a right stimuli. So there's a particular requirement that is stimuli to apply in order to trigger the shape recovery. And the recovery could be one time, one way, or could be reversible. That's called the two-way shared memory effect. Typically, shared memory alloy, because this originally this term shared memory effect actually is from the invention. Sorry, the finding shouldn't be a kind of particular invention. Should be finding from a particular type of alloy, and until later on, nickel titanium alloy was invented. Then this become shared memory material become hot kind of topic for I think for over 50 years. And the next type is shared memory polymer. You may wonder that shared memory polymer doesn't mean that.
Professor Huang, we cannot see your slides, so you can share your screen.
Sorry, you.
Yeah, we
okay.
see
Sorry.
Yeah.
Okay, sorry, I forgot to share it. Sorry.
Okay. It's okay. Yeah.
Okay, so now it's okay now?
Yeah.
Okay, sorry.
Yeah.
Okay, so quickly show this is the video. Yeah, okay. Shared memory alloy and then shared memory polymer. Actually, shared memory polymer shouldn't be a particular type of polymer, because shared memory polymer, because most of polymers, they are heating responsive and chemical responsive. They have this kind of shared memory effect. And if you go back to biopolymers, which means that even DNA has a shared memory effect. So shared memory polymer is not limited to particular type of polymer, but the shared memory effect is a feature of most polymers. Could have long history if we back to the origin of these human beings or beyond that. And the next is a shared memory composites. Shared memory composites, according to my definition, in the composites, multiple materials are combined together, at least two materials combined together. One of them should be the shared memory material, either alloy, polymer, or some other type of shared memory material. That's called the shared memory composites. So the additional material is used to enhance certain features of the composites. And next is shared memory hybrid. Hybrid it's different from the composite in the sense that, according to my definition, that is of course hybrid means that it includes more than one, two or more, this kind of parts. And each individual parts within certain working environment, individually they don't have a shared memory effect at all, but if you combine together, it has a shared memory effect. And of course, there's some other materials, for example, shared memory hydrogel, blah blah blah. Hydrogel depends on the water content. If it's dry one, that is under the category of shape memory polymer. If it's wet ones, of course, water plays an important role. The next is advanced shape memory technology. Advanced shape memory technology. The term of shape memory technology was invented, I think in 1994, around that, when shape memory alloy. At that time, there's one organization currently called SMST. They kind of regular meetings, and the term shape memory technology was invented from there. And that refers to the shape memory alloy. But now, because shape memory polymer become more popular now, and therefore we can see that utilize the special features of polymers, and also we can extend the intrinsic feature of alloys. And then we can come out with a kind of advanced shape memory technology. So the additional features included are listed here to enable the shape memory effect in materials, which means that you can see to enable shape memory effect in materials is not limited to shape memory material, so that we can expand it to many kinds of materials, including conventional engineering materials, in particular engineering polymers. As I just mentioned, that most of polymers has a heating and chemo responsive shape memory effect. So what is heating responsive? What is chemo responsive? Later I'm going to explain. The second is that to design materials with required shape memory functions. So this is particularly interesting because most time we have particular requirements for particular application. So most time we may not be able to easily identify or find such a kind of material. So how are we going to, instead of synthesis, particular kind of material, that could be kind of tedious work. Can we design materials with the required shape memory function? So this is another particular feature under this advanced shape memory technology. The next is to optimize the shape memory performance, which means that we have the material there. Almost everything is okay, but there might be something which is which does not meet the requirement. For example, the activation stress is a bit less than requirement. So how can we actually improve it with the existing material? So this is to optimize the shape memory performance. So from the whole life cycle of products, from design, fabrication, and later on repairing, and finally recycling, we all can utilize advanced shape memory technology. Okay, the first is this basically is many years ago, MEMS application of thin film shape memory polymers, shape memory alloys was quite popular. And then this basically is nickel titanium deposit, sputtering deposit on top of silicon. So that by passing current through the thin film to heat up jaw heating, we are able to have these two top and bottom parts close open. This is kind of micro gripper. And this video basically illustrates step-by-step recovery of a piece of nickel titanium shape memory alloy strip. You can see upon gradual heating, it recovers in a step-by-step manner. There is another way, instead of step-by-step, segment-by-segment recovery. This is another way which is only applicable for certain type of alloys. In shape memory polymers, they're called triple shape memory effect because upon heating, gradual heating, it bends uniformly down and then becomes straight again. So this under shape memory polymer, that's called a triple shape memory effect. But in fact, this is achievable in shape memory alloys as well. This is a similar kind of triple shape memory effect, but this time we use shape memory hybrid. That includes silicon as a matrix, and the inclusion is VEX. Of course, programming plays a very important role over here. And another case of step-by-step recovery multiple shape memory fab is showing over here. This is a PMMA acrylic. We can program it in a certain way so that upon gradual heating, the top part drop, and then this part, and then step by step, it recovers its original shape. Okay, so finally, it turns to be a kind of flat piece again. All right. And lastly is that we can have multiple circles impressed on top of this polyurethane. And upon gradual heating, the circle disappear one by one from outside towards inward. Okay, so basically we can see these are heating responsive shape memory fab, either direct heating using hot water, or otherwise we can use so-called indirect heating, the joy heating, by passing a current through the nickel titanium piece. Okay, potential application areas of my interest including actuators, sensors, active assembly and disassembly, medical applications, in particular for minimally invasive surgery, and the next quite interesting topic that is called smart manufacturing, but we utilize shape memory fab. One is, of course, is so-called 3D, 4D printing. So from 3D printed piece, and then we can, while different ways, one of course is utilize the shape memory fab. There are other ways. So we can convert a 3D printed piece has the additional function that is called shape change. So that's called a 4D printing. It actually very depends on how we pre-deform the piece. This is a quite complicated topic. So I'm not going to extend too much about that. The next is more of my current interest. That is called one size for body temperature comfort fitting. And then solid state UV cross-linking for rapid manufacturing anywhere, anytime. Instead of using liquid material for UV cross-linking, we use a solid material instead. For actuators, we have a list of all these basic mode. We can utilize one-way shape memory effect, one-way shape memory alloy for one-time shape memory effect. This based actuation or cyclical shape change or cyclical shape memory. I'm not going to go through all those actuators. I'll show you a couple of examples. The first is buttons on demand. We have a shape memory alloy piece inside of this. Now let's see. We pass current through the shape memory alloy, dual heating one time. So we come out with a pop-up as button, and then we heat up again. It becomes flat. So the button's on demand. When you want it, the button appear. But if you want to get rid of, make it flat, then you can just heat up again using pass a current through it, joy heating. We can utilize this kind of mechanism together with shape memory alloy for actuation to make a high heel, which, as you can see over here, the height of high heel is able to be. We actually have the mobile phone, which is able to activate the change of the height of the high heel. So it's going to be more convenient. And next, you can see the height difference, which is about half of the original height. The next is sensor applications, flexible shape memory, RFID. The RFID, if you can embed the inside of, for example, polyurethane, and then you can heat up and then roll into another shape. And this shape, temporary shape, either you heat up for recovery. First, of course, it's flexible because this polyurethane is quite flexible. And secondly, is that if you roll into this shape, nobody can read it. I mean, the frequency, of course, is different from the original. So because it is inside of embedded inside of polyurethane, it's waterproof, And the surface roughness can be controlled so that you can your finger to feel where this piece of RFID is. And another application is that we combine the shape memory effect. We enable the shape memory effect in those kind of lenticular lens. So at the very beginning, the words are not clear, but upon heating, you will see this 无效, these two words. From one side, you can see one character, and then from another side, you view it, you have another character showing over there. And next is anti-heat transfer label. Okay, sorry, let's start from very beginning. Okay, this is a normal anti-counterfeit label, void paper. If you try to remove it, it's going to be damaged. Of course, we know how to get rid of it. You can heat up and then remove it without causing any damage to the label at all. So this comes to be a problem. The next is that we modified from the existing void paper, and this time if you heat up, it's going to damage the pattern on the surface of the label. So it's a combination with the heating responsive shape memory effect together with the void paper function. It's a kind of sensor, but this for anti-counterfeit application. The next is that we can come out with a design with using silicone, soft silicone, and for example, some body temperature program material. So we can come out with your fingerprint captured precisely. This is a comparison using the shape memory hybrid we developed, a body temperature programmable one, and compare with the VEX. So you can see these two are almost the same. And what potential application of that? We can use this to unlock those device, whatever is ultrasonic, capacitive, or acoustic scanners. For example, the mobile phones. We can come out with this kind of material with your fingerprint on top, and then we can use this to open your locked smartphone. The next is kind of watermark. We have a piece of PMMA acrylic, but we can program it in press using two sides of the coin. The coin. Basically, we program twice at different temperatures. Upon gradual heating, the top one basically is normal photo, and the bottom one is a 3D surface scanning result. And upon gradual heating, you will see the surface from this side of the coin, and then switch to another side of coin, and upon further heating, disappear, and then become flat again. So this is original image, and the bottom one is the 3D surface scanning result. Okay, so here, this one, this side of coin, this pattern we can consider as a kind of watermark for further anti-counterfeit purpose. Right, so that we can have a very simple strip, compress it at high temperature or a certain temperature. So we can use this kind of very cheaper, low cost, the kind of label as a kind of temperature sensor placed on top of individual part or individual items. So if the temperature is over a certain temperature, is able to recover its original shape or flip over to another side of the pattern as shown over here. Right, so this is a kind of temperature sticker, low cost, and then you can reuse it as well. The next is assembly using one single sized PMMA rod for a range of size holes, which means that one size for all, but this time is to fix two parts of the components. Before heating, the diameter is smaller, which basically stretch the PMMA, and then place inside of the hole. After heating, these two parts assembled precisely together. Of course, if the inner hole is threaded, so upon heating, will come out with this kind of thread, and therefore you can use a screwdriver to remove it And here, this is a short video demonstrate how we come out with the shared memory screw. So this is a sample. We have a polyurethane sample. We have pre-stretched it, place inside a hole, and upon heating, compression, then we come out with a screw, shared memory screw. You can heat up again and then remove it. So this is for active assembly and disassembly. The next is about medical application of shared memory material. Here we use PEG. Basically, we cross-link PEG and we come out with a wire, and we pre-stretch it significantly, 500% in this particular case, and then we place inside of room temperature water. What might happen to that? Yeah, actually, this is kind of water-induced buckling. This is called chemo-responsive shared memory effect or water-responsive shared memory effect. And the potential application of this is we can use this water-induced shared memory effect, significant buckling. We can come out with a kind of degradable, this kind of plug to block blood vessel, as demonstrated over here. Within 2 minutes, the tube is fully blocked. We use water as the most convenient medium to activate the shape recovery. We don't need heating. We don't need anything else. And the time to start the buckling effect, we can control it. Okay, so in this case, we have 2 tubes. And the bottom one, because it's blocked, so all the water is going to pass through the top tube instead of, for both tubes. And because this PEG is degradable, after a couple of weeks, it's going to disappear. So the block the blood vessel is going to open again. And the next is the animal test. We use rabbit, and we use this one, the pre-stretched piece of PEG. We can fully block the blood vessel in 2 minutes. But we have half a minute of time to check that whether the device is at the right position. Okay, so this is a biomedical application of PEG, pre-stretched. The others, including skin cleaning alcohol, activate self-tightening band-aid. We use polyurethane, and we pre-stretch the polyurethane, and we just using those alcohol to activate the shape recovery. So you can see this cut become much less. And here, this is after pre-stretching, and this is after wetting by alcohol. And this is the cleaning alcohol that we used. The next application is self-tightening, heating-driven surgical stapler. Here we use PLA. This is actually medical stapler. And all we need is we just heat up and stretching it. This basically is the original shape. Then we can heat up and then stretch the middle part a little bit. And upon gradual heating, it's closed. And at 48 degrees, it's fully closed. The most recent development about water-activated actuation is rapid hardening in room temperature water. This is a polyurethane from Dr. Hayashi. And the foam is a polyurethane foam. And this is the original shape. And we can use alcohol to soften it and then place inside of tube. After we take it out, we can see this exactly same shape as this part of the tube. We have different, this kind of examples showing over here. It's almost 100% capture the original shape of that particular type of the tube. So not only using water for activation of shared memory polymer, this time we actually use water to button to fix the shape. Of course, upon further heating, it's able to fully recover its original shape like this. The next topic is about smart manufacturing. I'm not sure how many of you heard about this kind of 4D printing. That was the term of 4D printing was quite popular nowadays. At the very beginning, 4D printing, the meaning of this additional D, there are very kind of ways to interpret this additional D. But nowadays, it seems that more and more we focus on the capability of the printed piece has the capability to change shape upon certain conditions applied. Okay, one of these is based on the shape memory fab. Mostly it's a shape memory polymer. From my personal view, if you print something using polymer and then utilize the shape memory fab to achieve 4D printing, shape change, that shouldn't be called 4D printing. It's just, whatever, use 3D printing to produce something, to produce a plastic piece. And the plastic piece, because of the shape memory effect of the polymers, so it's able to change shape after you program it. I would say that if you can integrate the programming, this part inside of the 3D printing, the process, 3D printing process, that we can call it 4D printing. Otherwise, it shouldn't be called 4D printing. But anyway, since this is one of the popular term, even we printed a piece, a 3D printed a piece, and then utilize shape memory fact in the subsequent operation. We still call it 4D printing. So this basically is based on the shape memory fact of polymers. Here, this is one example. I'm sure we all know who is this guy. We can use, for example, DLP to print this, and then heat up to the above the glass transit temperature of this polymer, and then roll into this shape. Upon further heating to activate shape recovery, heating responsive, it's able to recover its original shape like this very precisely. Another interesting kind of application is we have the original heart shape, this kind of cup. We can use a DLP to print it. And then upon heating, we can deform the cup into this shape. And then you put hot water or coffee inside of it, it's able to recover its heart shape. So this is utilize the shape memory fab. As I just mentioned, I don't think we should call it 4D printing, but unfortunately or fortunately, now this is one of the topic many people focus on this. The other is based on biostability. For example, we print a shape like this, and kind of structure design, we can push it, and it's able to switch to another shape. And this shape could be stable, so that you can heat up for recovery. That's called a kind of biostability based on the kind of 4D printing. And then we can have these multiple layers, 3D FDM printed. Of course, you need to use, for example, TPU or some other, this kind of nylon, this kind of relatively elastic material to print it. We are able to, each unit actually is a biostable structure, so that we can let it change shape from this basically is the other stable shape, this original shape. So we can achieve row by row recovery. And in fact, you are currently what we are doing is that we are able to control to let it go step by step, meaning that row by row is able to recovery. And which row is going to recover, we can actually control it. So this is what we are doing now. Of course, we need to use 3D printing, because otherwise, if we want to injection molding to produce it, we'll have a terrible problem because the cost is so significant. Of course, 3D printing is a very useful tool for R&D, but for mass fabrication, if we if you have hundreds, thousands, or 10,000 pieces to produce, I think that the quality, in order to control the quality of the piece, I believe injection molding is still the most reliable one. But of course, 3D printing, there are many other problems as well. Sometimes you have to modify the material a bit, otherwise, sorry, not only printing, but also injection molding. You will have a, for example, plasticizer, you have to include over there, otherwise you have a problem to produce it. The next is body temperature programmable elastic shell memory polymers. That is, this is a field I have been working on this for around 10 years. And the most recent achievement, including this tip over here on top of the earphone. Okay, this part where we use body temperature programmable elastic shell memory polymer, so it's able to fit the shape of individual, and you can reprogram it multiple times. So basically, this is one of the application of body temperature programmable elastic shell memory polymers. And you can compare the difference. Of course, this is not ideal because this basically is produced using 3D printed mold. The surface is not so smooth. This is the original shape, and this basically is after fitting. You can see the significant difference. And you may wonder that how nicely it can fit the individual, the inner channel of individual. And here we have utilized the SolidWorks to compare. This is a model, and this is utilize the similar material, not exactly same, but similar material. We can see it fit nicely to the model. And the difference we have actually checked. You can see occasionally here and there, there's some gap over there. According to our measurement, the gap is about 100 to 200 micron, which means that our diameter is about 70 to 100 micron. So the 200 micron means that slightly double the diameter of the hair. The next come for the fitting, but this time from elastic body temperature program material to this kind of hard version, relatively hard one. Probably you had experience utilizing this kind of splinter, shell memory splinter. But the problem with that particular material is because we need to use X-ray for cross-linking. So we come out with another way to get rid of this difficult part using, gamma ray for cross-linking. We come out with a version without cross-linking. We basically utilize the shell memory composite, this concept, to develop this kind of body temperature comfort fitting stuff. Another current research direction that is comfort fitting wrist keyboard. So here we go. Okay, we basically have the electrical circuit, stretchable electrical circuit, and placed on top of this. So it becomes a kind of device, a kind of keypad, which you can comfortably fit the individual. So this is a smart manufacturing because you can get rid of, include the previous one, the ear tip. You can get rid of the very complicated, tedious steps currently applied for smart manufacturing. Means that you have to individually measure the dimension and then get the 3D model and produce it one by one. But now you can come out with one size for all because you can utilize shell memory for fitting. And here is another example. This demonstrates the stretchability of the top, electrical part. This is a kind of touchpad, but stretchable instead of just flexible. It's a wireless version, so in the battery for activation, and is able to communicate with the the computer. And we have this kind of touch sensing function so that you can use this small piece to control the computer. We use only the commercially available material, low-cost ones, not the expensive ones, and highly reliable and washable. You can wash it. The cost is very, very low. We're talking about probably 100 renminbi or less than that for each piece, including everything. Okay, the next is we can also modify the surface of this kind of elastic shear memory material. So it has the function for cooling. Just modify the surface. So it's kind of power less cooling instead of you need to use power or some additional way for cooling. And this is basically compare the one side is modified, the other side is a flat surface, modified surface. So underneath the sun, you can see the difference in temperature. So one side here and the other side without modification of the surface. And the material is body temperature programmable elastic shear memory polymer. And this is shoe. In these days, 3D printed shoes become so popular. Almost any shoes companies, they try to produce it using DLP or some other ways to DLP, FDM to print the shoes. This was done at the very beginning. You can see the video is was made in 8 years ago by a part-time final year project student. At that time, we had problem to find a machine to print the whole size of this FDM printed to print the whole size of these shoes. So these shoes was printed in 3 parts and then glued together. But I believe this should be the first 3D printed piece which can wear. And because we use a polymer, so it has a shear memory effect, but not precisely body temperature fitting, but it's able to change the shape slightly. Okay, and then so to conclude this part, we can see this kind of one size for single size. We don't need to individually come out with the model of the individual to measure the model, just 3-dimensional model of the individual piece. And we don't need to produce it precisely, but it's able to comfortably fit. If it's a human body, shoes, or some other device, it's able to comfortably fit the individual. Because we don't use TG, glass transition temperature, for shape memory fat. We use crystallization and melting. The next topic is a solid state UV cross-linking. Instead of using liquid, now this liquid resin, this time we use a solid resin. But the beauty of this solid resin is that if it's high temperature, it's easy to flow, just like liquid. But at low temperature, it is solid. So here we have an example. Yeah, just like dough, but depends on the hardness. Actually depends. So we can, deform it into any shape and then use UV to cross-link it. After cross-linking, it becomes so hard. Right, so this basically is a solid state UV cross-linking. You may wonder that what are the advantages of solid state UV cross-linking? The first, of course, it's solid, not liquid. So it's easy to transport and low cost. Cost is much dramatically reduced and the storage is become much more easier. And the smell could be a lot less because the liquid ones, the evaporation of this very bad smell is going to be terrible. It's actually quite terrible. If you solid it, it's going to be a lot more less significant. And because it's solid to solid cross-linking, the shrinkage is a lot less, not liquid to solid. Okay, as shown here, easy transportation and storage, low smelling, and high precision printing, and no need for support structures because it is solid. And suitable for vibration and microgravity environment. So you can print anywhere, anytime, and at a low cost because this material actually is commercially available, the solid resin. And uncross-linked material can be fully reused. This is a lot more interesting to the actual application. So available materials, in addition to this particular version, which is as a kind of a hard version, we also have the thermal gel. We have utilized the F127. It's kind of a thermal gel to demonstrate the possibility. Solid state UV cross-linking. At the very beginning, we use this one material for demonstration. And later, we have come out with UV cross-linkable Vitramer. I'm not sure whether you heard about that. Vitramer is one type of polymer between thermoplastic and thermal set. So at low temperature is a thermal set with cross-linking. Upon heating to the melting temperature of the material is still able to maintain the shape. Until you heat up to much higher temperature, this reversible cross-linking disappear, so it becomes easy to flow. And it looks like a kind of thermoplastic. But it's different from thermoplastic because the melting temperature, if you heat up the material to the melting temperature, the material doesn't flow. The next is this kind of dual cross-linkable resin. Commercially available. We use this for this about demonstration. And of course, I just mentioned that we have this kind of solid state material which is able to UV cross-link, and we try to achieve solid state UV cross-linking for rapid 3D printing anywhere and at any time. So this is 2D setup. This is a machine for 2D processing, and this basically is the test inside our car. As mentioned, anywhere, anytime, rapid printing. Of course, we need to demonstrate that. We use this video to record the process. It's a bit too long, so let's see what we have printed. So this is these two are shapes that print out using this machine. And the cost of this machine is only $500. Sorry, 500 RMB, less than 500 RMB. Because we modify from the commercial laser engraving machine. The cost of that is about 70 RMB. And then we modified, replace the laser by a UV light. And of course, the next is volumetric additive manufacturing. So we are working on this using two UV beams. And the combination of these two beams, the result of that is after remove the uncross-link part, that is the 3D shape. Okay, and then the last slide. This is a video. Well, it should be something like more than 20 years, about 30 years. When I started working on shape memory polymers, we make this transformer. The basic idea is that if a car is too big, you have difficulty to find a place to park your car, so that we can heat up and shrink your car to the small size and place probably underneath a table. And then later, if you want your car back, just heat up and then recover its original shape. Of course, this is just for fun. Yeah, so this is after heat up. We modify from a tour car. The next is kind of 4D art lab, 4D Leti art. And the beauty of this is that it's able to swing, rotating on top of water, just water. And it's able to jump, it's able to swing forward, backward, clockwise and counterclockwise. That we basically utilize here the water responsive shape memory effect. And the membrane is edible, food grade. So this is another example for fun. Now, I think more or less that's all I want to share with you. So thank you so much for your attention. Yeah, thank you. Oh, sorry, the light is off. Okay, so that's all. Thank you so much.
Thank you, Dr. Huang, for this fascinating presentation. We now open the floor for the discussion. Anybody are welcome to share your thoughts, ask questions, and discuss ideas related to today's topic. Please click, you can click the raise hand button in your screen if you have any questions. Yeah, let me have a look.
So should I stop sharing?
No, you don't need. Um, there is no heart. Yeah.
Okay. Yeah.
Okay.
Okay. Okay. Yeah.
Okay. See,
Professor Yang.
Professor Yang. Yeah. Hi, Professor Yang. Hi, Professor Yang. We cannot hear you.
Okay. Maybe type a question here.
Yeah. Uh, I think the administration, Miss Han should open the microphone for Professor Yang. Okay. Can you hear me, Miss Han?
Yes, yes. Hello.
Yeah, Professor Yang Keke has some questions to talk with Dr. Huang. So you have made all of them to be quiet so you can open the microphone. Okay?
It's open. It has been open.
Okay, let me have a look. Hi, Dr. Yang, can you hear us? Yeah, you can speak. We can hear you. Okay, then we need time to take some questions. So I have a question, Dr. Huang.
Yes.
In the development of robotics and AI, what
Mhm.
do you think about the unique opportunities of chip memory polymers in the coming decades?
Well, very good question. Um, um, Also, it's a very hard question. Um, I can tell you one thing that I share with one thing. What I asked a question. Professor Otto Suka. He was top guys in the field of shape memory alloys. He retired many years back. I once upon a time I was in Kyoto and met him there and asked him after his retirement, um, asked him one question: How do you? What's your opinion or advice to us as a senior researchers in the field of shape memory alloys? Not limited to shape memory polymer, but of course, uh, um, um, my research field covers both shape memory alloy and the polymer. And he replied to me, he said, application, application, application. He's a top guy working on one of the top guys working on fundamentals of shape memory alloys. But when he retired, he's more interesting in this kind of. He feels more interesting to explore the applications of the materials. I think this is should be the same. Shape memory polymer is a lot hot as compared to shape memory alloys now. Um, so can we learn something out of it? You mentioned about the AI. I believe currently, if you search using AI to help you to understand some topics, for the fundamental part, no problem at all. But if you want to explore deeper, if you have your research in the frontier of the particular field, you will find that no. Um, it AI has a limited knowledge of it, but of course we can utilize AI help us to do some kind of data analysis that we have done. Um, we spend the time to study the shrinkage of electrospinning, those kind of textile material, and we found that actually is due to the buckling of those kind of wires. Actually, it's kind of thread. And so we use AI help us to identify the key issues here. In particular, can we control the shrinkage of from both direction to control the shrinkage of that? What are the control parameters? So for this, I feel quite comfortable. But there's one point I have to mention. Research-wise, for AI, they want a significant amount of data, but experimental-wise, we can't afford to do it. At the very beginning, we have probably 100 sets of data. We feel that's quite enough. I mean, enough in the sense that it takes that much time to fabricate and test it. But for the student, well, another student, he take care AI analysis part. He always replied that data is not enough. Okay, I believe this could be the kind of gap. How we are going to fill it. So AI is useful, but can we put our current situation? We have my personal feeling is that AI is helpful, useful, but we still have something advantage as a human being that AI won't be able to easily take over our job. So we can relax a bit. Probably in the next couple of years, we are still okay. But after 10 years, with more and more knowledge, the AI build up, then we may have some kind of troublesome because the AI may be able to to do a lot more. So So my personal opinion is we should use AI, but at this stage we can't rely solely on AI. So probably we can together work together with AI, and in particular those guys use AI to to get something done. But from long term, I believe AI should take over human being. But within the short term, it may be over some 5 to 10 years. So we still have time.
Okay, thank you. It's very promising. Yeah, I think AI can help us to design new shape memory materials, and they may promote each other. And yeah, it's very interesting. Yeah.
Okay, thank you. Okay, the question is that the surgical stapler. Yeah, surgical stapler we use PLA. That is commercially not commercially available. And of course, that is using glass transition temperature, but somehow I think it's kind of medical grade PLA. They probably modify a little bit because you can see it's not that brittle. Most PLA is quite brittle. I believe it's a modified PLA, but I'm not sure how they modify it. Of course, it's kind of secret. We won't be able to get any information from the manufacturer. So that is using, yes, glass transit temperature, but the glass temperature of this PLA is much lower as compared to like the kind of filament. The filament the TG is about 60, 65 degree, but this one is only 40 plus.
Thank you.
Okay.
Can you hear me now? Let's have another questions about you said the solid UV cross-linking use the thermogels.
Mhm.
If there's a need, the material must be transparent for this
Yeah, sure.
UV cross-linking.
Not necessary to be so transparent because DLP to print ceramic. Of course, the reason even is fully transparent mixed with this kind of particles. It is not so transparent, so we still can use DLP to print it. SL DLP are able to print it without much problem.
Thank you.
So it's not necessary to be transparent.
Yeah.
But for volumetric, yes, we may need a very highly transparent material because it's go deeper inside of the material.
Thank you. Thank you very much.